Hi guys, welcome back to Quantum Quandary. Today we've got the Gaussian integral. It's a pretty easy one to solve. We can just rewrite the dummy variable as another one. See what I did? I just said that x and y, it doesn't matter, and it gets integrated over anyways, so all we get is some number. And now I can do just I times I, right? And then I can just take this first one, multiply it by the second one, and I end up getting a product of the two integrals. Now, since they're dummy variables, we can, just mix everything up, put everything under the integral signs. Gonna write dx dy first, like a physicist. And then the arguments, which can go up together, because, exponents can add. Yeah, there we go. And this is pretty much the last form in the Cartesian plane that we need. And now we need to go to the polar coordinates, because to integrate over this, we want to, introduce a substitution. But if we introduce the substitution now, it just won't work. So we need the polar coordinates. This is an area element, right? Dx dy. So if we've got like the Cartesian coordinates like this, and then let's say this is x, and then this is some y. Now the Cartesian coordinate system, its changes are isomorphic? No, not isomorphic. Isotropic. The changes are isotropic. They're the same everywhere, right? It doesn't matter if you're at x equals a or x equals 0, the change in x is going to be the same everywhere. So we can just show a change dx and a change dy, right? That's the total change. And then this area element is dA if you multiply dx times dy. Right. Okay. Now, if we choose the polar coordinates where r squared is x squared plus y squared, then this same thing, I could draw this as r, right? This would be r from the Pythagorean theorem. And then if I wanted this kind of area element, this would be my dr. And now I wouldn't have exactly the same shape, but in infinitely small sizes, it really doesn't matter. So let's say that we go by some angle d theta. This is the angle. Well, actually I should draw it here, over here. This is d theta. Now this arc length over here that we're going to cover, it's actually going to be proportional to r d theta, right? Technically, it would be r plus dr times d theta, but that's a second order change, which would, in the limit become 0. So this area element here, wow, is just this is our dA. Here it's dx dy, and here it's dr times r times d theta. Okay, so that means that we know how to change our dx dy, and we also know that this is our x squared plus y squared. What we're missing are the bounds, right? So x and y are going from minus infinity to infinity, both of them. Now r is limited to positive values, right? So what we have in the polar coordinates are just a bunch of concentric circles as a grid, right? And our r, it rotates together with theta. So actually we just want to cover the whole polar plane. So we want to cover theta from 0 to 2 pi, right? Well, this is pi. We want to go all the way around, right? Yeah, and then r just goes from 0 to infinity, and we have r encompassing the whole circle. So where we had x, y from minus infinity to infinity, we now have r from 0 to infinity and theta from 0 to 2 pi. So now let's just rewrite this integral. Yeah, it's I squared, right? So it's I squared is the, two integrals, 0 to 2 pi and 0 to infinity. We have d theta first, and we can integrate that immediately. And then we have r, well, yeah, let's put dr times r e to the minus r squared. Yeah, so this is one integral that we're going to evaluate. The d theta part is the other. So d theta, we just get 2 pi. And then we're gonna need a substitution. Let's introduce, no, times 2. Oh, actually, times 1/2. And then we have dr times 2r e to the minus r squared. And now all I need to do is say that r squared is u. The bounds are the same. U goes from 0 to infinity. And dr times 2r is du. So this guy becomes du. And I just get 2 pi. Well, I can get just pi. Canceling with the fraction. I have du times e to the minus u. Pretty simple integral. It's pi minus e to the minus u from 0 to infinity. At 0, it's 1. And the minus sign from the difference gives us a minus, so it fixes the plus. At infinity, it's 0, obviously, so we get that I squared is just pi. And that means that I, which was the integral of dx e to the minus x squared from minus infinity to infinity, is pi. And that's our result. That's the one we were looking for. Okay. Hope you guys enjoyed the video. Leave a like, subscribe, whatever. Bye-bye.